T12.14. Growth hormones are often used to increase the weight gain of chickens. In an experiment using 15 chickens, 3 chickens were randomly assigned to each of 5 different doses of growth hormone, 0, 0.2, 0.4, 0.8, and 1 milligrams. The subsequent weight gain in ounces was recorded for each chicken. A researcher plots the data and finds that a linear relationship appears to hold. Here is computer output from the least squares regression analysis of these data. Assume that the conditions for performing inference about the slope beta of the true regression line are met. Part A, interpret each of the following in context. All right, so part 1, or the first item there, is the slope. So in the computer output, the slope is this value here. It's in the coefficient column. It's the last coefficient in the coefficient column. All right, so the slope, think back to your days of Algebra 1, it's the rate of change. It's how the y variable changes with respect to the x variable. Okay. Or we could say that for every 1 unit increase in the x variable, the y variable is predicted to increase by 4.8. Okay. Now, of course, I didn't use any context there. I'm going to be replacing the variables x and y with dose and weight gain. Right, so Roman numeral I. Okay. For every 1 milligram increase in dose, the predicted weight gain will increase by 4.8323 ounces. The second item is the y-intercept. So graphically, the y-intercept tells us the y value when the x value is 0. Okay? Or in this case, it's going to be the predicted weight gain when there is 0 growth hormone. All right. In the computer output, the y-intercept is going to be the first value in the coefficient column. I'll label that A. Remember the formula for a regression line is y hat equals A plus bx. So A is the intercept, B is the slope. All right. So when dose equals 0 milligrams, the predicted weight gain is 4.5459 ounces. Okay. Now you'll notice that in both of these interpretations, I'm using the word predicted weight gain. I'm not talking about the actual weight gain because our regression lines help us get predictions. Okay, they don't tell us the actual weight gains, the actual values. All right, the third item is the standard deviation of the residuals. That is this value right here. It's labeled as S. Okay. You can think of this number as the average prediction error of the model, right? So we're using this model to make predictions. We need to be realistic and know that these predictions aren't going to be perfect, but there's going to be some degree of error to them, and the error is going to be about 3.135 ounces. So we can say, not so, predictions from this model will be off by, or on average, or yeah, let's phrase it this way, will be off by about 3.135 ounces on average. Okay, and I realize I'm missing the context there, so I should say predictions of weight gain from this model. Okay, so let's do that, predictions of weight gain. The fourth item there is the standard error of the slope. So first of all, we usually refer to that using the notation SEB, and that's going to be the value next to the slope in the computer output. So SEB is right there. So this number tells us how much the slope of the sample regression lines vary from the true one. Right? And so you can imagine that they only did an experiment with 15 chickens, right? And maybe they get that slope. But maybe they do an experiment a month later with another 15 chickens, and the data looks a little different, and they get that slope. And then maybe they just kind of repeatedly do this experiment, and then they just get a bunch of different regression lines, right? These are all sample regression lines, and they all have slightly different slopes. Okay? But there is going to be one true regression line, right? If we were to do an experiment on all possible chickens, right? And that true regression line is going to have some value of its slope. I'm trying to represent it with this green line here. Okay. So SEB is basically measuring the amount of variation of all these of the slopes of all these sample regression lines away from the true slope. So let's say the slopes of the sample LSRLs relating dose to weight gain typically vary by 1.0164. And now the units, because this is a slope, the units are ounces per milligram. Right? Ounces is the units of the y variable, and milligrams are the units of the x variable. So the slopes of the sample regression lines that relate dose to weight gain typically vary by 1.0164 ounces per milligram from the true regression line, from the true slope, or from the slope of the true LSRL. Okay. All right, that was part A. That was a long question. Part B, do the data provide convincing evidence of a linear relationship between dose and weight gain? Carry out a significance test at the 5% level. All right, so let's start with choosing the procedure. This is going to be a t-test for slope. Okay, our significance level is 0.05. Our parameter is beta. Okay, so here beta represents the true slope of the population least squares regression line relating dose to weight gain. All right, the statistic is 4.8323. Okay. The null hypothesis is that there is no linear relationship. Notationally, that's just saying beta equals 0. No linear relationship. The alternative is beta is not equal to 0, suggesting that there is a linear relationship. Yeah. Now, you might be wondering at this point, how come we didn't write the alternative hypothesis as beta greater than 0? And the reason is because the question isn't asking us to find evidence of a positive linear relationship. It just says find evidence of a linear relationship. So that means we're looking for evidence of both positive and negative. So we're doing basically a two-sided test. All right, we do have some evidence for the alternative because the statistic, the slope of the sample regression line, is greater than 0. Okay. Now the question is this because there really is a linear relationship, or is this just by random chance that it happened to be greater than 0? All right, we don't need to check the conditions because the question said that we can assume the conditions are met. Okay. So I'm going to jump right into the calculation step. So we'll begin with the general formula. Okay. A standardized test statistic is a statistic minus its corresponding parameter divided by some standard deviation. In this case, we're doing a t-test, so we're going to get a t-value. The statistic is b, the sample slope. The parameter is beta, the true slope. And we don't have the standard error, but we have the next best thing, which is the, we don't have the standard deviation, but we have the next best thing, which is the standard error. Okay, so we'll be using the standard error there. All right, so 4.8323 minus 0, remember the null hypothesis states that the true slope is 0. And then SEB is 1.0164. All right, so this is going to give us test statistic 4.8323 minus 0 divided by 1.0164. All right, so that gives us a test statistic of 4.75. Just want you to realize that it's right here in the computer output. So I didn't really have to do anything on the calculator. It's already part of the output. 75. All right, let's draw a picture. Okay. So a t-distribution is mound-shaped and symmetric, like a normal distribution. This is going to have degrees of freedom n minus 2. Okay, there were 15 chickens in the study, so 15 minus 2 is 13. All right, centered at 0. Okay, 4.75 is going to be out there. Remember, this is a two-sided test, so we're actually going to find the area in both tails. So to the right of positive 475 and to the left of negative 475. All right, I can find this on the calculator, right, because it's a t-distribution. I can use t-CDF. Let's do the right tail area. So 4.75, and we'll do 99.99 with 13 degrees of freedom. Okay. So the area of just the right tail is that value, 1.89 to the negative 4. Okay. But then I'm going to double it because there's also the area in the left tail. So times 2. Okay. We get 3.79 times 10 to the negative 4. Okay. 3.79 times 10 to the negative 4. All right. Notice that that's basically, what we have in the computer output. If I rounded the value that I'm getting on the calculator there, that way, if I rounded that to one digit, it'd be a 4, right? Because the next digit is a 7, so the 3 would round to 4. Okay. Anyways. All right, so there's our p-value. Let's see, are we missing anything in the calculate step? Got the general formula, specific formula, plug in the numbers, picture, test statistic, and the p-value. Okay, everything looks good. So now we're going to write our conclusion. Okay, so that p-value is small. So since 0.0004, I'm just going to round it, is less than 0.05. We reject the null hypothesis. So there is convincing evidence of a linear relationship between dose and tweaking. All right, so that was part B. Part C now wants us to do another one of those 4-step processes, but this time constructing a confidence interval. All right, let me see if I can just move this over. Just move it down here for now. Okay, and give myself some space to do part C. All right, let's do it in another color. It's blue. All right, so in the choose step, the procedure is a T interval for slope. Okay, confidence level 95%. Okay, we already defined the parameter, so let me just copy that. I don't want to have to write that out again. And I think that's all that's needed for the choose step for an interval, right? There's no hypotheses here. We're not doing a test. We're making an interval. Okay, we're going to skip the check step because, again, we're assuming the conditions have been met, and then go straight to the calculate step. So our general formula is a point estimate plus or minus a margin of error. In this case, our point estimate is B, the sample slope. Our margin of error is a critical value, that's a t-value, times the standard error of the sample slope. All right, so we already know B is 4.8323 plus or minus, okay, our critical value, all right, 95% and 13 degrees of freedom. Let's go to T distribution. Okay, so 95% and 13 degrees of freedom is 2.160. It's hard to show you there, but it's 2.160. 2.160 times 1.0164. Okay, so let's go ahead and calculate the endpoints here. So 4.8323 minus 2.160 times 1.0164. Right, so one endpoint of our interval is, let's just say 2.64. And then the other endpoint, I'm just going to change this minus sign to a plus sign. Get 7.03. All right, and now we just need to write a conclusion. We are 95% confident that the interval from 2.64 to 7.03, and now the units here, remember, these numbers represent values of the true slope, and the slope is a rate of change. It's the change of y versus the change of x. Y is measured in ounces, x is measured in milligrams, so this has units ounces per milligram. All right, so the interval from 2.64 ounces per milligram to 7.03 ounces per milligram captures the true slope of the population LSRL relating dose to weight gain.